Welcome back to the deep dive. So today we're kind of leaving behind the world of simple point masses and forces.
We are. We're diving into how real continuous objects respond to forces, things that can bend, stretch, and distort.
We're talking about elastic materials.
Hmm.
It's the physics of how things deform and hopefully snap back.
And that's a huge challenge, really, because how do you talk about forces inside a solid object, everywhere at once?
Right, it's not just a single force vector acting on a dot anymore.
Exactly. Our mission today is to build up the mathematical language for this. We need to define local distortion, which we call strain, and then connect that to the internal forces, which we call stress.
And this language involves tensors. First, the tensor of strain, to describe how things stretch and shear, and then the tensor of elasticity, which is this huge dictionary connecting that distortion back to the forces. So let's start with the basics. How do you even describe a distortion?
So the starting point is to just imagine a tiny speck of material inside a solid.
Okay, the one little point.
And we just frac how it moves when the whole body is deformed. We use a displacement vector, let's call it us, that just points from its original spot to its new one.
Simple enough. So if I take a block of, say, gelatin and just stretch it in one direction, the x direction.
A homogeneous stretch.
Hmm.
In that case, the displacement in the x direction is just proportional to how far along the x-axis you are.
It all stretches uniformly.
Right. And that gives us the simplest piece of strain, the fractional change in length. We call it xx. It's just how much axis changes as you move along x.
And I assume you have the same thing for the y and z directions.
You do. I and s. Those are your three stretch strains.
But things also shear. I can imagine taking that same block and pushing the top surface sideways so the square faces become parallelograms.
That's a shear. And in that case, the displacement in the x direction actually depends on your y coordinate.
Okay, and this is where it gets a little tricky.
This is where we hit a really critical distinction. When you measure that kind of motion, the raw numbers you get could describe two different things. A genuine distortion of the material, or just a pure, simple rotation of the whole block.
Wait, I'm a little stuck on that. If a pure rotation doesn't cause any internal stress, why do we even have to worry about it? Why not just measure the distortion directly?
Because you can't, really. The raw mathematical description, looking at how all the displacement components change with all the coordinates, gives you 9 numbers.
Okay.
And that description naturally includes rotation. A block spinning in space has those mathematical components, but obviously its atoms aren't being stressed relative to each other.
So we have to find a way to mathematically throw out the rotation part.
Precisely. And the insight is that genuine strain is described by the symmetric part of that 9-component description.
Meaning the shear from x to y has to be equal to the shear from y to x.
When you enforce that symmetry, you are left with only 6 independent numbers, 3 stretches and 3 shears. That's the strain tensor.
And the other part, the antisymmetric part.
That describes the pure, stress-free rotation. So for elasticity, we just ignore it.
Okay, so we have our 6 numbers that perfectly describe any local distortion. Now we need to build the bridge. How does this strain relate to the internal forces, the stress?
This is basically a giant 3-dimensional version of Hooke's law.
Where force equals some constant times the stretch.
Right. But now, every single one of the 6 components of stress could, in principle, depend on every single one of the 6 components of strain.
So that simple constant K, it's not so simple anymore.
Not at all. It becomes a massive connectivity map, a 4th-ranked tensor called the tensor of elasticity. And if you do the math, 6 inputs and 6 outputs, you start with 81 possible coefficients.
Whoa, hold on a second. 81? You're telling me I need 81 separate numbers just to describe how a random block of something bends?
Well, in theory, for the most complicated asymmetric crystal you could imagine, yes, it sounds completely unmanageable.
It sounds impossible to measure.
But this is where the physics of symmetry comes in and does this beautiful simplification. The work you do to distort the material has to be stored as potential energy inside it.
Okay, that makes sense. Energy conservation.
And that one physical requirement forces symmetries onto this giant tensor. It immediately cuts the number of independent constants from 81 down to a maximum of 36.
Okay, that's better. Cut by more than half.
And it gets better if your material has some internal symmetry like a cubic crystal. Think table salt or iron.
Right, a repeating lattice structure.
That structure reduces the number of constants all the way down to just 3.
3. From 81 down to 3.
And for a completely uniform or isotropic material, something like glass that looks the same in every direction, you only need two, the Lamé constants.
That's just an incredible simplification, all from applying physical symmetry to the problem.
So this whole framework isn't just for things sitting still. It also tells us how elastic bodies move.
Dynamics.
Right. Now we have to balance the internal forces from stress, not just with external forces, but also with inertia. Mass times acceleration.
So we're looking at Newton's second law for a tiny little cube of this material. But wait, stress is force per area, right? It acts on a surface. How does that translate into a push on the whole tiny cube?
That's a great question. It's a classic physics move using a bit of calculus, Gauss's theorem specifically. You can convert the total force from the stresses on the surface into something that depends on how the stress is changing inside the volume.
So if the push on one side of the cube is bigger than the push on the other side, there's a net force.
Exactly. It's the spatial derivatives, the gradients of the stress that create a net force density.
Okay, I think I've got it.
So now we combine everything. Newton's second law, this force density from changing stress, and our generalized Hooke's law, connecting stress to strain.
And what comes out of all that math?
What comes out is the wave equation. And what's amazing is that it predicts that any elastic solid has to support two, and only two, fundamental types of waves.
This is the big payoff.
It is. The first type is a longitudinal wave. This is where the particles of the material move back and forth in the same direction the wave is traveling.
Compression and rarefaction, that's just a sound wave, right?
That is a sound wave traveling through a solid. The second type is a transverse wave, or a shear wave.
Where the particles move perpendicular to the wave's direction, like shaking a rope.
Precisely. And the theory doesn't just predict they exist, it gives you their speeds. And those speeds are different, determined only by the material's density and those two elastic constants we talked about.
Which is fundamental to things like seismology, understanding earthquakes.
Absolutely. It's one of the most powerful predictions to come out of the theory.
That is beautiful. But it all assumes this perfect linear relationship, that things always snap back. Real materials break.
Right, they fail. We've been living in the nice linear part of the stress-strain curve.
I'm picturing that graph. At first, it's just a straight line. Stress goes up, strain goes up proportionally. That's Hooke's law.
That's the elastic region. But then, if you pull too hard, you hit a point.
The yield point. The curve suddenly bends over.
And after that, you're in the region of plastic deformation. The material is now permanently changing its shape. The atoms are literally slipping past each other into new arrangements.
And the strange thing is, the material keeps deforming even if the stress doesn't increase much or even goes down a little.
Exactly. And eventually, you reach the breaking point, and how it breaks tells you a lot.
You mean like the example with the piece of chalk?
It's a perfect demonstration. If you pull a piece of chalk straight apart, that's tension, it snaps cleanly right across.
Perpendicular to the force.
But if you twist it, which is a shear stress, it doesn't break that way. It breaks along a 45-degree helix.
Which seems weird until you analyze the stress tensor.
Right. The math shows that for pure torsion, the maximum tension is actually acting along that 45-degree line. And chalk is weak under tension, so that's where it fails.
It's a fantastic visual proof of how the components of stress work.
And then, of course, you have materials like, saran wrap or other plastics that has memory. Their response depends on how fast you pull them. That's viscoelasticity.
Where you have both elastic springiness and internal friction, or viscosity.
It adds a whole other layer of complexity where time becomes a factor.
Okay, so this has been an incredible journey, from a single displacement vector all the way to waves and material failure. But here's the part I find the most satisfying.
Connecting it all back to the atoms.
Exactly. Can we really derive these macroscopic constants, those 2 or 3 numbers that define a material, from the simple forces between atoms?
We can, and it's the final proof that the theory is on the right track. Imagine a simple cubic crystal, like salt.
The perfect grid of atoms.
And we can model the forces between them as little springs. A spring constant, K1 for nearest neighbors, and maybe another one, K2 for the next nearest neighbors.
So it's just a lattice of masses and springs.
It is. And we do the same thing we did for the continuous material. We apply a uniform strain to this whole lattice and calculate how much potential energy gets stored in all those little springs.
And I'm guessing the final equation for the energy has to look just like the macroscopic energy equation we had before.
It has to match perfectly. The energy density is some combination of the squares of the strain components.
So you just compare the two equations, term by term.
And when you do, Out pop the expressions for the three elastic constants of that cubic crystal. They are defined directly by the spring constants K1, K2, and the spacing between the atoms.
That is the ultimate connection. The stiffness we measure in a lab on a big block of iron comes directly from the stiffness of these conceptual springs between individual iron atoms.
And the numbers work out. When you calculate them for materials like sodium or iron using this model, you get values that are remarkably close to what's measured experimentally. It's a huge validation of the whole tensor approach. Hashtag outro. So to just recap, we really built the whole machine for elasticity. We started with a way to describe local distortion, the symmetric strain tensor with its 6 parts.
Then we connected it to internal force using that giant but ultimately simple elasticity tensor.
And that framework didn't just describe static bending, it predicted something profound: the existence of both longitudinal and transverse waves in solids.
For me, what really stands out is the power of symmetry. It just cut through the complexity. It took us from an unthinkable 81 constants down to 2 or 3 that are physically meaningful.
I'm sure they come right from the atomic level.
So here's a final thought for you to take away. We've just explored the beautiful, complete mathematical world of perfect elasticity. But the real frontier, where things get messy and fascinating, is in that non-elastic region. Understanding the physics of plastic flow and fracture, how materials truly fail atom by atom, is still one of the biggest challenges in modern material science.